Okay. Last day. Listen up. Last day we talked about charging by contact. All right? If I charge up my Wimshurst machine, and we're going to have to do this for our experiment. If I charge it up, give it a good charge. Oh, that was sad, but it's still a charge. Just be patient. Oh, our experiments are going to struggle. Our experiments are going to struggle today, and I'll explain why in a moment. If I charge this up, and again, I'm going to put a label out, but this is negative and this is positive, and I touch this sphere to it, I can transfer some electrons to it. That's charging by conduction. We already covered that. If I touch it with my hand, I'll transfer those electrons to my body and ultimately to the ground. What we want to talk about today is really the primary way in which charge can be separated or charge can be formed. And that's by friction. I switched around the notes because we got talking about making our pith balls and charging them by touching things to them. So now I'm going to talk about actually the most fundamental way in which charge gets separated. And that's by two things rubbing together. All right? And that's what we mean by friction. You've already seen this note. You don't have to write this down because I made you write this down the last day. I said to you that there are three primary ways of doing this, and one of them was by contact, and the first one I already covered was B, touching one charged object to another and causing the electrons to transfer. Now I'm going back up to talk about really the most fundamental way in which we can separate charge, and that's by friction. Two objects rubbing together. Two objects made up of two different materials, okay? And when you have objects rubbed together, you can easily remove charge. So, come on, advance, you can do it. Why are you not advancing? You can write that down. Number one, charging by contact, A, friction. And unfortunately, we're doing this backwards. We already did B on Friday. We talked about contact. Now, I plan on drawing a picture here, all right, as I usually do. Thoughts that could be inside your head, Jess? That's a better place for those. That's Remember, I said that the electrons are out in orbit around the nucleus. The nucleus is locked into place in the substance in which it is. But because the electrons exist on the outer surface, if another substance comes in contact with it and rubs it, it can supply the energy needed to pull the electrons away. So electrons are very easily removed. If you decide to continue on in chemistry, you will learn that certain atoms can actually pull harder on electrons than other atoms. The pull is not an even strength scenario. Each atom has different numbers of protons, and therefore some atoms pull harder than others. And then when you put them into compounds like this little piece of acetate, this is an overhead sheet that I cut into a strip. And if we then take a look at a substance that we can rub it with, like this silk, at least I think it's silk. I really don't know if it is or isn't. I'm not good at identifying these substances. But if I rub them together, one of the substances will pull harder on the electrons than the other substance. And when that happens, electrons get transferred, okay? So I'm not sure how I'm going to draw this. I should have maybe practiced this. This could be a great big mess. I'm going to maybe draw a substance. Maybe I'll draw a substance like, how am I going to draw that? I'll draw it like a rod of some sort, like that, okay? Or maybe the acetate strip, okay? And I'll draw another kind of substance up against there that's maybe the silk. Doesn't really matter what it is, okay? And 4 positive charges are required or will be confused. Is that correct? 4 positive charges. 1, 2, 3, 4. And at this point, it's neutral. 1, 2, 3, 4. And we'll do the same here. 1, 2, 3, 4. 1, 2, 3, 4. And we are going to rub that object along the surface of the other object. And when that takes place, electrons can be transferred. Now, to be honest, I have no idea which way the electrons move on silk and acetate. You're going to try to do an experiment in a moment where you're going to rub various substances together and try to determine which one became positive and negative. I really don't know what it is on this pair. But one will transfer the electrons to the other. Let's put that maybe as, let's just have this guy transfer it this way. So I'll put my arrow that way. All right? And I'll put the E negative in there. E negative. There's the electrons moving. And in the end, I'm going to have the rod. It's got 1, 2, 3, 4. And let's have it gain 2 electrons for no particular reason, just to keep the numbers nice. 1, 2, 3, 4, 5, 6. Okay? And in the end, the rags over here, whether it's silk or not, it's got 1, 2, 3, 4. And how many electrons have I got left on the silk, Jay? 2, 1, 2, hangs out near the middle. And the math kind of works for this as well. We started out with a charge of 0 and a charge of 0. And notice, what did we end up as our charges? What's the charge on the rod? Jess? -2. And what's the charge on the silk? I think Jess is getting it. +2. And does that make sense mathematically? It does. We started with neutral. Remember, our sum was neutral, and now we've got it opposite charges. Yes?
I have a question.
Let me just talk about this. Notice the one that loses the electron becomes positive, and the ones that gain the electrons become, oops, look at that. Oh, look at there. It ended up over there. That's terrible. Become negative. All right. Okay, Jess, your question?
On this picture, it's contained with 5 positives.
Yep.
Does that mean that one of the positives can move to the other one?
No, no. The reason I made 5 positives is because these pictures are just representing very simple structures. In reality, this piece of metal, I believe it's probably a chromium alloy, has got how many, Jay? Which means it doesn't really matter how many positives I draw, but what would you think if I drew all of my pictures with 18 positives? Would you be happy?
No.
No. So the 4 has no meaning there.
So either way, the positives can't move.
Correct. They're locked into place in the center of the atoms. Write down electrostatic series, but you do not have to draw this chart. If I'm going to make you use the electrostatic series, I will supply you with the chart. I want you to write down the words. I'm going to put some examples out there. Then there's a couple of homework problems, but like I said, we're then going to move on to an experiment. We're going to test this electrostatic series. And it's not going to work very well, and I'm going to explain to you why it's not going to work. But that's okay. Doesn't mean we don't do the science. Someone has rated various substances on how well they pull on electrons. All right? This is a chart that I simply took out of the textbook. Human skin. I don't know where they're getting that. You know what I mean? Human skin. So like, so that means if you rub your hand up against your hair, the skin has a weaker pull on electrons and the hair has a greater pull. That's what they're implying. I guess we could do a part of the experiment where you rub your hand on your hair, but it may not work very well. And I'll talk to you about why. Notice that at the top, these guys tend to lose their electrons. These guys result in a loss of electrons, and therefore they become positive. These guys tend to gain electrons and therefore become negative. So in my example, if I were to take some acetate, and acetate is just a fancy name for a type of plastic that we use for overhead projectors, and I were to rub that up against some silk, right? And you can think of it like a battle. I put the acetate up against the silk, and I rub them, and I generate a static charge. What do we predict should be the charges on the acetate versus the silk? According to my chart, what should the charges be? Now, Parker, you paying attention? Yeah. Excellent. These guys lose and they tend to become positive. Okay? These guys gain and they tend to become negative. All right? I am rubbing the acetate up against the silk. What charge is the acetate going to become? What charge is the acetate going to become? Travis, what do you got? It's going to become positive because it's going to lose electrons. It's going to become positive. The silk should become negative because it's going to gain electrons. Yep?
This is probably going to be wrong. So I'm just going to say it anyway.
Okay, sounds good.
So in reality, you can't actually get a number of positives and negatives.
No, because they're coming off in piles and billions of them. We're not going to be able to. We're only going to be able to detect positives and negatives.
I think the numbers.
Well, we're going to have to try it without numbers. What if I took that acetate and I put it up against something called, let's call it polyester. Polyester. Acetate versus polyester. What are the charges going to be? Okay? Which will be a stronger charge? Which pair, acetate versus silk, and acetate versus polyester, which will result in the stronger charges? A greater number if we could see the numbers. Which one would result in a stronger charge? A bigger number if we could see the numbers, but we can't. What do you think? And why is that? It's not that they have more negatives. It's not that they have more negatives. Yep. Well, remember, the acetate becomes positive. Your argument's correct, but you've got it backwards. And why will this be greater, though? Why, you're right. It's true. But according to my chart, why would it be greater? Jess? Yeah, but I've got acetate here, and then I've got my silk here, and then I've got my polyester here. I would say that the silk's higher up on the chart. What about their separation on the chart? How far? Yep.
The polyester would be twice as negative.
Well, you want to say it's twice as negative because you want to count things.
Yeah.
But we can't do that. But we could say it's going to be more negative.
Yeah,
because they're further apart on the chart. All right? So this will result in a stronger charge. All right. Let's now get set up for our experiment. I'm going to stop this recording. What's that? No, I got to explain to you what's going on.